Hi, this is Piers Ridayed, CEO of Radix. I'm here with Dan Hughes, founder of Radix, and we are going to be trying a new format going forwards. We're going to be trying video AMAs on a bi-weekly basis rather than just in the channel. Dan always has so many pearls of wisdom, and a lot of the time, unless you're in the channel at the precise moment that he appears, you don't get all of the joy of seeing his answers. So what we're going to be doing now is I'm basically same format as before. We're collecting the AMA questions for Dan, but I'm now going to be asking them to him and following up, and he's going to following up with any things that might come out of that. So the format is going to be quite simple. I'm going to read the question. Dan's going to come back with the answer. There is one question for me in here, which we'll be doing the reverse. And if there's any points of contention for us to discuss or anything that comes out of that, then we'll dive into those details as well. So the first question that we have is: other projects like Xian, Elgorand are taking cautious steps about their sharding deployment on their mainnet. E.g., Xian is currently in single sharded, and they plan to enable 4 shards in the coming days before proceeding further. Though Radix doesn't follow a dynamic adaptive state sharding process, do you anticipate that there will be minor milestone releases before Xian, which follows similar approaches that other projects have taken? Mr.
Dan. Okay, so the state model that we will likely end up with, it doesn't really have any concept of shard groups or replica sets or validator sets. It's just there's this piece of state, and it should live in this place in the shard space, right? So shard space 2 to the power 256, and then you have a piece of state, and it lives in a particular place, right? Now, how you orchestrate the responsibility of chunks of that state, which is what I currently call a shard group, that's a lot more flexible, right? So to make the state model have some constraint around, how many shards there are, right? So let's say that we said, okay, instead of going for crazy 2256 right now, we'll go for 8. To change that later at the state model level is well, it's a lot of work, right? Because then you've got to do a lot of work to reorganize all of the state into the newly sized shard space. So it's easier to say instead, okay, well, if we want to take baby steps, then let's just say, okay, for this particular release, there can only be a maximum of 8 shard groups, right? And then those shard groups will have a quantity of replicas and validators within them. So potentially we could baby step out, but from the state model, applying constraints there is just a ton of complexity to then grow it out later on. So it's better to do it from your replica and validator sets and constrain them instead. It's probably a sensible thing to do, at least for the initial release of Xian. And going with a small number of shard groups, say we went for, say, 8 or 16, right? And let's say that each shard group, even conservatively, can process a couple of hundred transactions a second, then you have possible throughput of a few thousand initially, and then changing that parameter is much easier then. So you can say, okay, now we'll go to 32, and all the replicas and validators in those current shard groups just then, just redistribute, and more shard groups pop up. The quantity of shard groups can be dynamic, so just put a cap on it.
Right, because you're also dealing with the sort of the whole deterministic data mapping set for the network, and like one of the things that make it so powerful is this idea that you do have a deterministic data mapping which tells you which shard something's on. So you want to start off with the number of shards that you kind of want to continue with, and so what you're saying, if I understand it correctly, is you're saying it will start with probably from Babylon onwards, right? It's going to start with 2 to the power 256 shards, but the first version of the network, all nodes have to operate all shards. They can't drop any shards. They can't only be doing a subset
you just
of it.
One shard group, right? So that's it.
Right, and then as you go towards Xian, there can be experiments, because Xian is really testing that cross shard consensus and state state sharding, state replication between nodes that don't necessarily have a full picture of the ledger, which is where the real complexity comes out, right?
Yeah. So it's sensible to say, okay, let's just cap the number of shard groups initially, so that if there are any glitches or bugs that need to be fixed, unraveling that spaghetti across 4 or 8 shard groups is a lot easier than doing it across, say, 100, right? Because you've got a lot more crossover going on.
Cool. Awesome. Next question. So this question is a twofer. I'm going to be combining 2 questions which actually have a lot of overlap in the answer. So lots of discussions recently about what defines atomic composability. It could be argued that asynchronous cross-shard approaches like Elrond could be defined as atomic, as they are still all or nothing. Is Radix able to achieve full synchronous cross-shard composability? And if not, what is the biggest differentiator Radix has with regards to composability? And then on the second, the follow-up, which is a bit deeper, but it's the same concept, same question sort of, on state provisioning versus state yanking. State yanking, obviously what people like Elrond do. Is Cerberus state provisioning like state yanking? Is there a crucial difference that it is part of the same consensus algorithm instead of spread across multiple ones?
Yeah, this is a question that touches on a lot of points, and the answer is somewhat subjective depending on who you ask as well, right? So in the broadest sense of atomicity, then you could argue that approaches like Elrond and other asynchronous cross-shard models, even though they're asynchronous, you could say, well, they are atomic, right? Because either everything happens or nothing happens. But that's the broadest sense of atomicity, right? The kind of atomicity I'm talking about is where you have an event that needs to execute, and all of your validators and all of the replicas that may not even be validating, they all can execute all those state transitions at the same time, right? Or loosely at the same time. So I'm talking within, a few hundred milliseconds of each other. So you essentially have them kind of synchronized to execute. And the output of all of those executions across all of those different shards and state transitions, they are all processed and happens at the same time as well, right? When I say same time, I mean, a small amount of variance because you'll have some latent nodes and whatever. But so long as, your super majority of validators across all of the shard groups that are responsible, as long as they execute in the same round, let's say, right?
Yeah, within consensus time, within a single round.
Let's say that our execution bound is within the same consensus round. Then that is what I would argue as being atomic in this sense, right? So everything runs parallel. All of the different validators and replicas and whatnot in all the different shard groups, they're all agreeing or disagreeing on the output of this consensus at the same time, right? Even though they may be doing some bits and pieces of it asynchronously to each other, you have these two kind of synchronizing events that happen. The first one is to agree to actually execute the event. That's quite loosely synchronized. Then there's a much tighter synchronization that happens. And the interesting thing with these synchronization events is that they kind of just happen as a consequence of what the Cassandra protocol is doing, right? So this is what Cassandra's doing right now. So the second synchronization event is actually on execution, right? Now that's much tighter. So when you actually have an execution, the majority of the validators that have to execute whatever it is that's happening will do so within a few milliseconds of each other. It's really quite tight, assuming of course you've got nominal network conditions, right? You haven't got liveness breaks going off here and there and all this kind of stuff. Under normal conditions, they execute very close together. And then the kind of synchronization event is when the output then gets confirmed in a consensus round. So that's kind of what I feel like the minimum definition for atomicity in this kind of domain is, right? So everything happens in parallel. You've got these naturally synchronizing events that synchronize up the validators who are going to be executing things. And once you've executed, you've obviously got state locking going on as well. And that essentially is a stricter definition, a stricter implementation of atomicity, right? It's not something's executing a piece over here, then it stops and it waits, and then it goes somewhere else, and something else is responsible for executing some other piece, and then that's over, and this is over multiple consensus rounds in multiple kind of shards or subchains or whatever, right? And it's very serial.
Right, because then you also have this concept. If it's not if it's actually true finality rather than probabilistic finality, you have this problem of like something being final locally, but not being final at a global state
there's
level.
There's so many different nuances that can trip you up. This is the problem, right? So like, what if something goes wrong in one of the other execution domains on a different shard, right? Or there's a liveness break over there. Now, if I was the first set of validators or replicas to execute this thing, right, and there's a liveness break over there, I don't know anything about it because, as far as I'm concerned, I've done my piece, right? So then you have this additional complexity that has to go on top for detecting these liveness breaks, or for communication to come back to me that, well, this piece and this shard went okay, but this piece didn't, so we need to roll back, and all. It just gets very complicated when you're doing it serially, right? And then if you have a strong adversary who can maybe take advantage of some of those things, right? Well, if I can get in the middle here, I can make that set of replicas think that it was all good, and I can make this set of replicas like lose liveness maybe.
Right.
And then you would potentially end up in a situation for a safety break as well, which just complicates everything. Right. So, I mean, yeah, like, a lot of these things are solvable, but the problem with it is that when you start to build complexity on top of already complex things, you just end up with more surface that can break, right? There's more opportunity for bugs, there's more opportunity for things to go wrong. Analyzing and testing just becomes a lot more time consuming and a lot more difficult as well. So
the difference here with Radix is if I'm understanding correctly, is essentially that the finality, the commit phase, is essentially synchronous across the network.
Essentially synchronous,
and that is what means that it either all commits or it all doesn't, and it doesn't mean that you can have any part of the network that is final when another part of the network doesn't consider it to be so.
Yeah. So once you're past the execution stage, right? So let me back up a little bit. So what a lot of protocols do is that they have some event, maybe it's multi-shard, whatever, right? And when it gets committed to like a block, let's use blocks, it gets committed to a block, and then it gets executed, right? And then if there's another piece somewhere else, then that goes into a block and that gets executed. And the way the Cassandra execution and state model works is it's a small difference, but it gives you a ton more flexibility, right? So let's say that I'm in validator set A and you're in validator set B, right? So some event comes in, yeah? And then I look at that event and I see, right, there's some state in there that I'm responsible for, and there's some state in there that you, Piers, you're responsible for. So what we do is we do a little bit of gossip across our validator sets to agree that we like this event, right? The signatures are fine, it's a proper form, any kind of constraints on variables like overflows and stuff like that, all good, right? So then we both agree that, yeah, you know what, we will accept this atom, right? So there's like this concept of an acceptance. And so then we both go and do our various consensus locally that we're doing. And let's say that locally, me and my other validators, we accept this event into a proposal that gets consensus, right? Once that happens, we don't execute right then. That becomes a promise to execute, right? And this is the nuance. Yeah? Instead of executing, it becomes a promise to execute. So from a client's point of view, when that happens, we're saying to the client, okay, some point, hopefully soon in the future, we will attempt to execute this event that you want us to do. And at some other point in the future, you will get a final yes, no answer on this, right? So the client gets that information, whatever, via an API call or something. And so from the point of view of the replicas and the validators in my group A, we then take this event and we go, okay, we'd like to execute this, but we need to provision the state first, right? Now, provision means we go and read the state from wherever we need, right? Different from state yanking. So like state yanking is the responsibility of managing the state moves from one place to another, right? So, and if we were doing state yanking, if you had some state that this event needed, before we can execute that event, you and your validators in group B we would have to agree that group A takes responsibility for that state, right? So then you collect all the state in one place, and that just opens up a bunch more complexity as well, right? It's like, okay, well, who's got this state now that I currently need? Is it B or is it A? Is it C? What happens if I don't get that state? What happens if you send me this state, but then I have a liveness break, and so I never actually officially receive it in terms of my own ledger, right? My own shard.
Right. It's like, oh, I delegated it to B. Did you? Because B doesn't think you did.
Right. So there's all those kind of problems, right? So state provision is I'm just simply reading. So no state moves or anything like that. So I've got this event and there's some state there for me. So I'll lock that state. I say, right, okay, this state is locked. I'm not going to do anything else with this state until I've finished executing this event, right? This is the simplest form. I'll keep it simple. So it's simply just Cardano style, right? Got this event, nothing else can happen with this state until it's been executed and it's been committed, right? The execution output has been committed. So then I read locally the state inputs that I need, and I send them to you, right? And this is going on with the other replicas in both of our shard groups. But I gossip it to you. I say, hey, Piers, that event that we loosely agreed on that we were going to accept and attempt to execute, I'm ready my end. Here's the state inputs for me that you will need. When you're ready your end, can you send me the state inputs that I'm going to need to do this execution, right? And then sometime later, you locally have a proposal that includes that event, and then it gets committed. It's a promise to execute from your end. You send me the state inputs. You've already got mine, right? So at that moment, we have a synchronicity event, yeah? Because now we both have the state inputs that we need, so we can both execute at that moment, right? So that's why it's quite tight. I can't execute anything until you have sent me your state input. There could be 100 other groups involved in this, but none of us can execute until we have state inputs from your group, right? So you have a really tight synchronization on the execution. Now, once I've got your state inputs and you've already got mine.
Just as a side point, which is why the parallelization of consensus operations on Radix is so important, right? Because you could have this event that's happening across a large number of shard groups, large number of validator groups, but it doesn't stop anything because the separation of state information is so broad across all of the shards. You're essentially not waiting for one shard to complete before the next operation. The likelihood of there being two operations waiting for each other in order on a shard is basically almost impossible.
Doesn't matter here. Yeah,
it doesn't matter at all. So the fact that you may be waiting a little bit longer to finish a very large state, consensus operation synchronicity event
has no impact.
Has no impact on the ability of the rest of the network to continue, which is also a massive difference between Radix and a large number of other networks.
This was one of the really kind of deeper research points of Cassandra, right? Because you've kind of got Cerberus and the cross shard stuff that's defined in there, but it doesn't get into the execution model or the state model or anything, right? It's just how do you reliably and safely communicate state transitions across shards, right? But from an execution point of view, the two things that really help us here and show the power of this kind of tech, the tech we've got as a whole, is that one, executions become a promise and hence completely asynchronous, right? Truly asynchronous. And number two, that asynchronicity of execution means you can still do tons of other stuff in the meantime, and that execution is just waiting for some state input to come in, right? Which also happens asynchronous. And the nice thing about this is that even though it's completely asynchronous, because of the nature of the execution, you actually get synchronicity as a byproduct on the execution, right? Because all the validators will execute at roughly the same time. So that's kind of state provisioning, right? Now what happens next is I execute, you execute, and internally within our validator sets, once we've executed, we do some votes, right? So you will do some votes with your local replicas, and I will do some votes with my local replicas, just to make sure that, okay, have we all got to the same output here? Does anybody disagree? Do we have a quorum on the execution? And importantly, do we have a quorum on the state that we're responsible for, right? Mm-hmm. So we vote, and if we get a 2f+1 agreement on those state transitions that I'm responsible for, then we produce what's called a state certificate. State certificate includes the input for the state that we were responsible for, the output of the state after the execution, and then basically a Merkle representation of the entire execution, right? So you can audit it if you want to. And then there's a quorum signature attached to that state certificate. And you're doing the same your end, right? You're trying to build these state certificates for things. And then we exchange state certificates when we've got them. Now, once we have state certificates, I then have, there's another step. It's called an event certificate, which is essentially just an aggregation of state certificates, right? So let's just forget that right now. Just to make it a bit more efficient to write to ledger and stuff. So what I've got now is I've got this bunch of state certificates from different places, and you've got a bunch of state certificates from different places. And the rules are either all of the validator sets responsible for all the state, either they all agree and it gets accepted, or if one disagrees, the transaction is aborted, right?
Yeah, one validator set, not one validator, but one validator set.
Yeah. One validator set, right? One quorum. So like if there was 4 state transitions in this thing, and I was responsible for 3 and you were responsible for 1, because we just, I don't know, a 2 shard group network. If you disagreed on yours, that would stop. That would stop the event. And the nice thing is that you can still put that on the ledger. So you can put an actual reason on the ledger as to why this failed, right? Because you have a certificate that says this failed, and you can, put a reason in there, what exceptions, whatever, right? So then we swap these things and we have these state certificates. And at this point, that's where this is where it becomes essentially atomic, right? Because I know that you've got a quorum, and you know that I've got a quorum, and you know that I'm not going to change whatever the input output of that state was for that event, right? Assuming, of course, that there is no kind of like really strong adversary that's taken over the network. Under normal bounds, you can think, okay, well, I've got this quorum certificate. I know that at some point they are going to commit that to the ledger, and those state transitions will be final, right? So if anything else comes in now on your end that wants to use that other piece of state, you can essentially use it, right? Because you've got agreement both locally and remotely from all the shards. Everybody knows what's happened on this event. So if something else came in now, even though you have that locked, you can, there's some tricks you can do so that you can get ahead of your execution a little bit. But let's just keep it simple, right? So, I'm just trying to explain this model. The problem with this question is, the problem with this,
you never get to say let's keep it simple when you're about this deep into a conversation about consensus.
Trust me, like, this is simple compared to some of these other approaches, right? This really is simple, yeah. Right. Because if you've got one failure case, either everyone agrees or nobody, or somebody doesn't agree, right? Somebody being a group. And that's it. You haven't got to backpedal. You haven't got to go and undo stuff. You haven't got to do loads of cross-shard communication to say, hey, this failed, that failed. What happened to that? Who's got this thing now? This is like simple, right?
I think that actually talks to a really core concept that is I really didn't get to appreciate until probably 2 years of working closely with you, which is that consensus is simple until it gets complicated. And what I mean by that is that the act of things agreeing is actually quite a simple process. The hard cases is what happens if the agreement breaks down at any point.
Yeah, the failure.
Every single failure case. So like creating a simple algorithm that allows nodes to agree as to what the state is, assuming no failure cases, assuming no timeouts, assuming no liveness breaks or like nodes going offline or whatever. That's really easy. And what a lot of the time happens is that you get things like, Elrond with stake yanking and stuff like that will describe the good case. They'll describe, well, look, this is what happens under normal working operating conditions. And you're like, that's fine. And it works as long as all of your baseline assumptions are there. But if you start talking about, well, what happens in the case that, like you say, the delegation isn't complete, a liveness break happens at some point during it. What happens if you have a large number of shards that have state locking and there's reliance on other transactions that are coming behind that is essentially locking consensus because you don't have this parallelization of consensus? Like, how does the state model change as you increase the number of shards, and like do all of that? How do you agree that the shard groups, the number of shards is increased, and therefore how the data mapping works? All of this stuff, that complexity, ends up being the thing that gets you. It's not how can I describe a system that works under good operating assumptions. It's how does it work under bad operating assumptions.
And the main problem there with this is that it's very easy to make complexity, right? Because you've got this nice, simple little thing underneath, and you catch an edge case. You go, oh, well, you know what? I'll just put a band-aid on that, and it's fine. But then there's another edge case behind that edge case, and it's like, oh, fuck, okay, well, I'll do that there, and I'll do that there, and then once you've got through all of the known edge cases, you've got this really nice thing in the middle, and it's just covered in fluff, right? And it's just doesn't look very nice. It doesn't work very well, because the core principles, what you should be looking at in the middle is not how do I get nodes to agree on consensus. It's how do I get nodes to agree when shit's gone wrong, right? That's what you're really doing. You want solid agreement when things have gone south, right? And you have to. That's the only way to catch all the edge cases. You've got to be thinking fail fast, right? Everything is going to fail. Everything, even the simplest thing, right? Even incrementing this variable is probably going to fail because I'm a dumbass and it might overflow because somebody else somewhere is somehow managed to find a way to inject spurious crap into my memory because they're doing, some kind of chaos attack on the other side, right? All those things. So you just got to kind of, if you have a model that can survive all of those failure cases, then you get to the point with that model where it's like, okay, there's no band-aids on for any of these kind of, normal case, well-known edge cases. There's no band-aids for any of them. So then your probability of there being an edge case that you don't know about that can also cause havoc reduces dramatically, right? Because it's always the edge cases of the edge cases. You see an edge case, you put a band-aid on, but that edge case has got some nuance as well. And it's always them that get you. So it's like the second or third layer of edge cases that come and go,
right,
and blow everything up.
Right.
So
and I can remember plenty of times where we were talking like consensus back in Tempo days, and like I was early into it, and I thought, I'm a smart guy, I can work this out. And you were so patient. You'd just be like, I'd be like, well, why don't you just do this? And you'd be like, oh, Piers.
You drove me mad in those calls. Well, how hard would it be? Hard, Piers. Trust me. Hard.
I now have the curse of knowledge.
So anyway, there's one step left, right? So this is essentially a full breakdown of bird's eye view of what Cassandra's doing under the hood. So may as well finish it off, and then everybody's got a bit more information about what's going on until I finally get the blooming paper finished off. So we've got all these state certificates, right? And they have all the quorums, and it's an agreement or disagreement. It doesn't really matter, right? And the final step here then is that those aggregated state certificates that represent the execution of that event, they then go back into the consensus queue, right? So what's actually happening at the replica level is they're making proposals of things to execute, and they're also creating proposals that contain these state certificates on things that have executed as well, right? And so these proposals have some state certificates in. There's a round of consensus where locally the replicas and the validators are agreeing, okay, yeah, we're going to go with this proposal, because Cassandra is leaderless as well, so there's some additional complexity underneath. You could do a leader with a leader as well. Same principle, really. You just want some consensus on, we're going to write this to the ledger, right? We're going to write these execution state certificates and these events to the ledger in this order. So that's really what it's for. And once that's happened, then even though you have a kind of soft finality because you've got the state certificates, right? And you know that the state is locked, and you know that the transitions have been atomic across all of these shard groups. Once it's actually written to the ledger, then you have an explicit finality, and this actually happens quite quickly. So, in some of the testing I'm doing with Cassandra, with the Twitter stuff, right? Tweets are really, really heavy. You've got the kind of the event information, right? The hashes, and then you've got the user ID that's making the tweet, and then you've got any mentions that are in the tweet. You've got the counters for the retweets and the replies and the likes, and you've got all the hashtags and stuff, right? So tweets can touch 8, 9, 10 different pieces of state, right? So pushing a tweet onto the ledger touches them many shard groups minimum, right? And the finality time for a tweet of that kind of size, it's like 4 or 5 seconds at the moment. And this is with, a bunch of between 8 and 16 shard groups is what I've scaled up to so far. And anything from 8 to 16 replicas per shard. And so you've got all this stuff going on, and you're creating threshold signatures and signing them and verifying them and stuff. And a tweet goes in at around 4 or 5 seconds. And this is on optimized code as well. So there's a fundamental protocol that's going on here, like, the kind of cross-shard communication of state and all this kind of stuff that's going on, and then the asynchronous execution and all that kind of asynchronous voting that's happening there as well. It's the protocol is quite efficient, and that's a high level what's going on with Cassandra and how the state is managed and what the execution model looks like.
Which nicely brings us on to our next question, Mr. Dan. Is Cassandra is being used to demonstrate Dan's research work, but that will have a very different code base to what we have on mainnet right now. Does Dan oversee mainnet development to ensure implementation decisions made now won't impede his vision of what he wants the network to be in 5 years down the line?
Oversee is broad. So I don't go and I wouldn't be going.
It's also like it feels like it's a trick question. It feels like, well, if you're saying yes, you're like, well, how do you do both? And if you're saying no, then well, it's going to obviously be a problem.
yeah, I'm not going to go stand behind all the developers and be like, hey, that variable name, I don't like that variable name. It needs to be like, click the chicken or something, right? Right. It's not that. That's just micromanaging. No. So what I hope to produce out of this is a set of papers, some technical papers as well, right? So not just formal papers, but technical papers too. A reference code base, if anybody wants to. Sometimes code is better than paper, especially if you're a developer, right? Papers are long-winded and words, and 3 lines of code can represent 1,000 words on a page, right? But then just basically the blueprints for the development team, right? So that then when it comes time for Xian, and we've had discussions and we've agreed, whatever route we're taking, right? Maybe my state model needs some tweaks because some of the stuff that we want to do. But at the moment, I'm just working on a kind of very broad. This is an implementation. We can tweak things if we want to. They're discussions for later. This is a Xian that could be implemented. But from the development team point of view, they get all the blueprints, right? And then from an oversee point of view, they're probably quite high level, right? So I'd be in conversation with Matt and Ross and other senior developers maybe just to keep tabs on things. And if I wanted to, I could go in and look at all the pull requests that are going onto GitHub and stuff, right? So I can be as close or far away from it as I want to be, I guess. But at the minimum, high level is here are all the kind of the blueprints and the definitions and the technical papers and the code that explains how my implementation worked. And then, there's regular conversations at that point with Russ, CTO, Matt, and Josh, maybe, and whoever's heading up any kind of sub teams that are working on things.
There are important sync points as well, right? I think that like one of the things that we say quite often in Radix is this idea of does not preclude, right? It's not that you don't necessarily want to do it now, but you want to make sure that the mechanism by which you're doing something doesn't necessarily preclude doing.
No, yeah, I don't imagine it would be intrusive is probably the right word, right? I don't want to be like poking everything. I don't need to. The guys know how to build stuff, right? Like they built the mainnet with minimal input from me. Now, of course, if I need to be closer with Xian because there's stuff in there that is maybe I need to guide some people on, or I need to be a bit closer just to make sure that these particular pieces get done on point, then fine. But I don't expect to have to do that because the team we've got is solid. If I need to, or they want me to, then it's cool. I'll do whatever I need to. But at this point in time, they're the kind of bare minimum that I think I need to do. I don't think I need to go sit next to developers, for example. That would
right. And I think there's also like an important point here, which is that while you are an incredibly smart guy, you are not the only smart guy in Radix. There are some we have got an incredible team who when you sit down and discuss conceptual ideas and say, well, this is what needs to happen for a state model to work across a cross-shard consensus. That's often enough to run with and go, okay, well, we need to understand, like, these are the boundary conditions we need to work within, and then how do we design a specification that meets those boundary conditions, and from that point forwards, as long as at a conceptual level you're synced, it's fine.
They know what they're looking at, right? It's not like I'm giving this to some junior developer that's only got a year's experience under his belt in JavaScript, right? Yeah, I'd have to sit with that guy, and actually I probably wouldn't sit. You
would just beat him with a club.
I'd just do it myself, right? I wouldn't bother. But the guy, it's just a waste of time. I can move 50 times faster than that guy could.
Yeah,
right?
You love JavaScript so much, so I mean.
Oh God, I didn't start. But our guys on the team, they know what they're looking at, right? So I give them a technical paper about state models or execution environments or consensus or whatever, and they read it and they understand 99% of it, right? The 1% they don't understand is maybe where I've used stupid words because I don't like writing very much. So I can't think of the right word for
Dad?
that.
I invented a term.
Yeah, I can't think of the right word for that. Let's just make something up. Yeah. Google bagger. There you go. That'll do that. So I mean, yeah, like you wouldn't expect somebody to have to sit with a surgeon that was doing open heart surgery that was experienced, right? You wouldn't expect the head honcho of the hospital to sit there looking over his shoulder to make sure everything's going right.
Right.
He knows what he's doing. He just needs instructions on, okay, what's wrong and what the fix is.
Yeah. Consultation, advice, and fundamentally, as you put it, like running ahead of the team to catch the bullets that are coming down the line on future implementations of things like Xian. All right, let's move on. Let's move on to the next question, which is on scaling, on-demand latency. Radix claims to scale on demand. On scaling on demand latency, Radix claims to scale on demand. I don't dispute it does, but isn't the scaling only able to come into effect after the current epoch has ended? So, e.g., let's imagine.
I've answered this one before.
Oh yeah, you have, haven't you? Sorry, beg your pardon.
How's this one got in there?
Yeah. You have. You've actually done a long answer to that one. I'm not going to read the answer out. Yep. Okay. Next one.
Oh, it's for you. The next one's for you. You get to go. Okay. So, Piers, here's your question. On the spectrum of centralized versus decentralized development of the network protocol, how do you see development of the network protocol progress? Currently, it is centralized within Radix DLT, being the sole protocol manufacturer. This is fine in the early phase of the protocol, but will this change over time? Will it become more a community effort, not solely in the hands of a single team? I know it's open source and can be forked, but will the team at some point open the door for external contribution?
Yeah, it's a really great question. And it's something like some form of that has been sort of asked in many different ways. It's sort of like if you think about like any big open source project like Android as the operating system for mobile phones, or Linux created by Linus Torvald, there's this phase where you're just building the thing. Like in your mind, in the mind of the creator, there is this very clear vision of what the basic structure of the thing looks like. And as you're building that, it's very difficult to get external input, because you have to bring them not just up the learning curve of what your current thinking is inside your head, because it's not in code yet. It's not fully baked. It's not fully formed. I can't just open it up and go, oh, I understand what the full architecture of this. I understand how all components talk to each other. It's not there yet. And so you end up in this very strange phase, which is like this concept of task bounded rather than resource bounded, where you're like, I just have a bunch of things that can't be parallelized because they have reliance on each other. And this piece of thinking and logic and architecture has to be done before the next piece is done. And someone else can't work on something in parallel, this component over here, because this component relies on this. And at the moment, we're basically in the process of creating the thing on which everything else relies, every single piece of functionality, every single, like the way everything works together. And the best way of executing that is a very small focus team where everyone is up the learning curve. Like it can take us up to 9 months to bring someone up the learning curve to the point where they can meaningfully contribute within the Radix code base at the moment. But then there's the next phase, which is once you've got to here's the starting foundational piece of the network, sort of like the first phase that really comes into is post Babylon maturity. So like Babylon gets released, and then there'll probably be, there'll definitely be a bunch of like extra work to get the code base to a state where there can be external contributions. This includes like adding notes into the GitHub repo, like working out what sort of the strategy for validating and then including sort of external contributions is. There's also a really important point around community management where there's a lot of research into sort of effective open source communities, building effective open source communities, and one of them is response time. If someone comes in independently, opens the code base, goes, I can see a way I can help, independently builds a piece of contribution, and then that like pull request isn't responded to and doesn't have any answer, actually like within 48 hours is the big hump, because people get excited about a thing, they want to get involved, they do a thing, they've done all of this work, and then the team didn't even bother looking at it, and it creates this sort of like sense of like anger. We'll just look at my thing, and that can create a negative open source community around, and that can be just as harmful or difficult, because then that pulls the team out from having to actually execute to sort of doing more open source community management, which in and itself is a huge topic. So it will become much more of a community effort over time. I would see. I see some positives in how Ethereum does it. I see some negatives in how Ethereum does it. There's some great models out there. Like Android is a good model. A lot of Google tools like Kubernetes and stuff like that also have good models for community involvement. If you look at like open source communities like Drupal or WordPress, so there's plenty of good like sources to pull from in how you create a an engaged community of developers who are helping sort of build out a piece of open source code. But there is this sort of like difference between focused deployment and sort of like feature development. And at the moment, we're still in that sort of focused deployment, getting the foundations in place. So it's going to be a while, but it will come. And when it comes, we will be very have a very specific strategy of how we start to open up to community contributions and make sure the community, when that happens, feels properly recognized for what they're doing, rather than just like constantly angry that the team isn't listening to them, which can often happen.
Yeah, it's a big management responsibility, right? And that may not even fall on like Radix DLT, right? Anybody, like the responsibility of the code and the protocol moves over time. It goes to foundation maybe at some point. It's a huge undertaking to manage that. You'll have to have dedicated people that looking at the pull requests and reviewing the pull requests, and then there needs to be a decision about is this pull request coming in, but we've got another one over here that's doing something similar. Which one is better, right? Which is the best one that comes in? And so, I mean, it's a lot of work, but you can get a ton of value out of that if you can figure out a way to do it.
Right. And the other interesting thing about like these kind of communities is most people want to add new features rather than maintenance. Like code maintenance is a constant problem for open source code.
Yeah, bugs aren't exciting to fix.
Bugs aren't exciting. I want to be the person who created this new feature, and like
but if you want to get some clarity on a complex code base, bugs are actually the best way to get that, right? Because you're going to be trying to find a bug. You've got to understand very, very discreetly how all the little bits and pieces might be working that are causing this bug. So even though it's boring, fixing bugs, bugs is actually a really good way to quickly understand large chunks of a code base you've not seen before. So, there are benefits there, but still nobody likes doing bugs.
All right, let's move on to the next question. Thank you very much for that question. I have a further question on the subject of royalties. Are all royalties recorded? Are they available publicly, partially publicly, or not at all? That is entirely private. If they are available publicly, how fast and efficiently is this metric updated?
Okay, so some of the actual mechanics of how this will work at the ledger level is still in process. So this is going to be fairly high level. So it's just things like, okay, so the royalties, where do they live, right? Are they distributed across all the various shards? Do the royalties end up in the same shard as, say, the blueprint or whatever, right? But essentially, all the royalties, they have to be recorded, right? They have to be recorded so that the publisher of that component can claim them, right?
Right.
And they need to get consensus across the ledger, et cetera, et cetera, et cetera. And the royalties are public. Maybe there's some use case, when we actually get close to this and we're talking to developers, where there is some use case that they want to have some layer of privacy around who they are that are receiving them or how much they're receiving and stuff. But from the point of view of consensus, then they will all be on ledger and publicly viewable. So I mean, like, even if you can't see the amounts, let's say that developers don't want people to know how much they're earning on their royalties.
I wouldn't like even start going down that path right at the moment. Like, privacy is one of this, like, an extra.
No, sure. I'm just saying from the point of view of, I'm a developer and I want to use a particular component.
Right.
Then, but I can't see how much is being paid in royalties because reasons, right? Different reasons later on. But I want to know that people are actually using that component, so I can still infer how popular this component may be, because I can see how many royalties payments are being received, right? Even if I can't see the amounts. So you still have that metric of, okay, this component being widely used, or is there a different one that does the same thing that is more popular? So you could essentially use each individual royalty payment as some kind of rating mechanism, for example, right? If you wanted to have some form of,
I mean, it's a great rating mechanism, right?
Like, a great rating mechanism. Yeah. So to make those private, then you would need some additional complexity in order to be able to show how popular something is, right? Or how many stars it has or whatever. Right. So the royalties give you that for free.
So, all royalties are recorded on ledger, and all as a result, all of that information is available.
Yeah.
And how fast and efficiently is this metric updated? It's real time, because they are actual on ledger payments.
Yeah, it's real.
Right. Okay.
I mean, it doesn't like, the efficiency isn't impeded, because the call to that contract, that component, whatever you want to call it, that has to undergo consensus anyway. So you can bundle in the royalty payment with the call to that component. So it doesn't actually cost anything more in terms of computer efficiency. Well, a little bit, but nothing that's going to cost hundreds of transactions per second of throughput.
Right. It's not an extra payment to the execution estate.
It's bundled in already.
Next question. Are there plans to introduce time-constrained constraint component invocations executions without writing client-side code for timeouts? E.g., let's say, define a timeout behavior on execution of component at runtime to either commit, revert, timeout, transaction based on dynamic nature of parameters by dapp. So before you answer that question, could you just explain that question a little bit?
So I think what's been asked here is that a client can say, okay, I want to make this transaction, right? But if this transaction hasn't completed within a certain amount of time, maybe it's a time sensitive thing, right? So there's some arb over there, but I know that arb is going to go in a minute, right? I know it's not going to be there for long. So if this hasn't executed and completed in, say, 20 seconds, then just bail, right? Time it out. Don't do it. So then you can, because if you didn't have any kind of timeout mechanism, or a way to say, timeout in 20 seconds, that transaction maybe gets stuck in a queue. It doesn't execute for a minute. The arb's gone. You're left with a bag of stuff you don't want, right? So it's a very interesting use case. And I'm going to refer to Cassandra again here, because, well, it's what I'm using. And a lot of these concepts and things that are needed to do this are in there. So it makes sense to use it as an example. So one of the things that's been particularly tricky with cross-shard execution, right, in the manner that I explained earlier on, is, okay, what happens if something doesn't complete in time, right? What happens if something just gets stuck and it doesn't complete, right? It's in some shard somewhere else, some other replica set. I've executed it my end, but that other replica set goes quiet. So I don't get any state certificates from them for the stuff that they're responsible for. What do I do? Do I just sit around forever with this state locked and nothing else can ever happen on that state? Well, no, of course not. You need some kind of timeout, right? Maybe there's a liveness issue over there or something. So having a timeout mechanism that doesn't require any additional communication as well, which is very important, was another one of the big research points of this work in Cassandra. I think it took me about 2 months to actually figure out what is a reliable asynchronous timeout mechanism that I can use. So from the point of view of a Cassandra network, there is a default timeout length, right? So after, I think at the moment it's 2 minutes, just for testing. It can, it needs tweaking to find the optimal, but currently it's 2 minutes, right? So if after 2 minutes I don't have a complete set of state certificates signaling either accept or reject for this particular thing, then the timeout mechanism fires. And I won't get into the details of the timeout mechanism because that's another hour. Because it's simple, but it covers a lot of theory, right?
Right.
But there is no reason.
Another thing that before I joined Radix, I was like, if someone was like, timeouts are really difficult, I would have been like, what are you talking about?
Just stop.
Just stop. Just stop.
That's what you do. Yeah, no, Piers. So Cassandra has this concept of a timeout anyway, right? And currently it's set default. There's no reason why a client couldn't specify what that timeout was. So a client would say, okay, forget the 2 minutes, it's way too long for me, or whatever it's set to, right? I want this to time out in 10 seconds, right? If it hasn't been accepted, promise to executed, and then the result of that execution committed within 10 seconds, just time it out. So it's a small change in terms of what the network is doing, because it already has a timeout. Obviously, you want to be careful, because if you have a complicated event but you set the timeout really low, then it never has an opportunity to go through, because you still have some latency there, right? So there would have to be some kind of way of saying, okay, if your event does this, or it touches these many shard groups, you really don't want to set the timeout less than this, right? Because then the chances of it actually completing are very low. But yeah, you could have custom timeouts. You could set them really long as well if you wanted to. Probably wouldn't be ideal for some things, like a swap pool. My timeout is 10 minutes.
Right.
Okay, that's going to cause problems.
And also not. We're talking beyond Babylon here.
We are, yeah. I think you wouldn't have it on a client basis, right? Because that's just a massive security risk. What you would have the ability for, let's say I built a component, right? I'm getting royalties for it. Then the authority to set the timeout on events that come from that component, that would be the developer, right? So the developer would have the best idea of what are the best timeouts for this thing, right? Is this something that needs to be quite responsive? What are the bounds of timeouts, right? There's an upper limit, there's a lower limit and stuff. So you could delegate the responsibility of managing the timeout intervals maybe to your developer, right? Because they know best what that component needs in terms of timeout and latency.
I mean, there are plenty of users who it would be fine for. Like if you are actually an arbitrager, then just set up a server that runs that logic for your wallets, right?
From a user point of view, you would probably bound it and say, right, you can go you can reduce the default, but you can't go beyond the default. The default is tuned, right? You can go below if you want to. Shit might fail all the time, but you can't go beyond, because going beyond, you can cause liveness breaks with that, right? But the developer, you could say, okay, if you go beyond the default and you've got it wrong, it's only going to cause liveness issues on your application. It doesn't affect anybody else anywhere.
So I think we can mark that one as like area of ongoing research, but some good potential options.
Possible to do. Yeah. I might actually play around with that a little bit. That's a really good idea. But yeah, you could definitely do it. You just need to be careful how what permissions you allow, right? How far can you move it and stuff, and who can move it and under what conditions.
And then the last question is actually quite a simple one to answer. So good we left that one to last. The current iteration of mainnet requires, as I understand it, validators with a total of 67% of delegated stake to agree in order to reach consensus. Is there some quorum of actual individual nodes that is required? If, for example, 5 nodes had 67% of the stake, could they reach consensus even if other nodes were online? And this is specifically to do with our current Olympia mainnet, not really any of the stuff that we've been talking about during this call, specifically right now.
Yeah. So this is one of those things that you would probably have raised a number of years ago, as soon as we keep going back to when you first joined, and because just do this, just do that. How would it be? This is one of those things that seems like a good idea and simple in theory, right? But in actual practice, ends up.
Is that what I sound like in your head?
Yeah. You're, how hard would it be? And you know what? You've mentored Adam really well, because this morning before I came on here, I had a, hey Dan, how hard would it be, from Adam of all people? Leave the boy alone. Stop corrupting his mind with these. How hard will it be?
It's going up the curve. It's the process of going up the curve is going like, I think I understand the basics now. Now I'm trying to apply my knowledge in a way. Can I predict a behavior of the system based on what I think I understand?
Okay. So advice: if you have a how hard can it be question, the answer is probably hard, because if it was easy, it would probably have been done already.
The simple answer to this is yes.
So
it's five nodes with 67% of the stake could reach consensus. Yeah, yes.
It looks like something simple to do, but it just opens up a bunch of possible issues, right? So, what if, let's say you said, okay, 5 nodes, 67% of stake, but what if you don't have 5 nodes that have 67% of stake, right? What if?
Well, no. The question is there a minimum number of nodes? And the answer is no. There's not a minimum number. It's 67% of stake, and that's
too many edge cases, right? Because then you've got to really think about the configuration of stake, right? Yep. Who has it? Where is it? Yep. And it just becomes,
gets complex.
I can get into more detail on it if anybody wants to. I think we're almost out of time on this AMA anyway. So.
It's been awesome. Thank you everyone for the questions. There were a few questions that we didn't answer from this AMA that we'll come back to.
They're used to that, Piers. It happens all the time. It just the hour goes so quick. And talking is faster, right? But the problem with talking is when you're having a conversation, you say more words than you probably type. So.
But thank you so much, Dan, for your time. It's been great chatting with you, and we will be back again soon to do the next AMA. So have a wonderful day.